Hello, welcome to Maths with EJD. In this video, I'm taking the second area of NumPy, which is NumPy arrays and operations. In the first video on NumPy, that was the video where I talked about numerical computing with NumPy. We took an overview of the possibilities, the things NumPy can do. NumPy being numerical Python. So let's go. I like to start from this screen so I can navigate the way through to where the documents are. Yeah, so, and of course, in case this is your first time here, you should know that I have all these, the documents I use, the Jupyter notebook I use, you can find the link to them in the description box. And the essence is that you might download and then try your hands on the codes, tweak them, change things, see what you get, and then from there, you can actually get to deepen your knowledge about Python, especially scientific computing. So I go today. First of all, I share my screen, and then the next thing I move on to, talk about, I go to where my Jupyter notebook is, click on that, and the command line thing comes up, and then it leads to a local web kind of thing. It's more like, it looks like it's a web page, but it's actually a local host thing like that. And from here, I navigate to the desktop where my folder for scientific computing is. I go here. And today we have the ninth video under scientific computing with Python. And we're considering NumPy arrays and operations. In the first video on NumPy, that's the eighth video for scientific computing, we actually talked about some array stuff, but here we are focusing seriously on arrays and possible operations on it. Do you want to come along in this interesting journey? Of course, by now, if you have not subscribed to this channel, you want to be sure to do that. You also want to hit the notification bell so you can get alerted each time a new video is released. Of course, don't forget to comment if you need me to do something. Maybe you want me to quickly do something in a particular area or some math topic you like me to teach. Feel very free to do that. Comment, like, and share to others so that the community can grow and more people can know these things. All right, NumPy arrays and operations. Of course, you remember that NumPy is numerical Python, and it's particularly good for arrays and matrices, so to speak. So NumPy arrays provide efficient storage and manipulation of data compared to Python lists. So, before now, we had talked about Python variable data types and Python variable data structures. So the data structures store the data types. All right. So, and a list is one of the common things, the common data structures we came across in Python. So, that's like our first introduction to, working with some kind of array, like that. And, but here, NumPy makes it possible for you to be able to use a very high, like use bigger arrays and two-dimensional arrays because lists are just one-dimensional for the most part. Okay. So the first thing we want to talk about is creating NumPy arrays. How do you create NumPy arrays? Of course, it depends on what you want. What you want will determine the kind of array you create. For instance, you want to create a one-dimensional array. We did something like this in the first video. In the first NumPy video, actually. So I want to show the line so you can see I can refer to the lines easily. So of course, because we want to work with NumPy, the first thing you want to do is you import NumPy as NP. So NumPy is actually the main thing we need. It's the library, but then we import it as NP so that anywhere we need it, normally we should write NumPy dot something, but with NP, you just say, so like line 4 now, you need array is a function inside NumPy. So normally you should have written NumPy. So imagine you have to write everywhere you have NP here, you should have NumPy, but by using NP as alias, you can use NP instead of NumPy and it is still doing the same job. All right. So creating a one-dimensional array, that's what we have here, for instance. And here, what we actually are creating this NumPy array from a Python list, So you can use a normal Python list to create a NumPy array. We've done something like that in the previous video. So, for instance, you have array1d, like a one-dimensional array, right? And I say np.array is 1, 2, 3, 4, 5. So the Python list is 1, 2, 3, 4, 5. So we turn it into a NumPy array with this command. And this array1d is just a variable name. So you can now print NumPy 1, you can now print array 1D, and it, of course, it just comes out like this. You could also use the tuple like I demonstrated in the previous video. Then, of course, you can create a two-dimensional array. So to create a two-dimensional array, one thing you can do is you can create that from a list of lists. For instance, this whole thing here is a list containing two different lists. So the first list contains 1, 2, 3, and the second list contains 4, 5, 6. So with this now, you can actually create a NumPy array that is two-dimensional. So by the time you run this, you have a matrix, which is 2 rows and 3 columns. So row 1, row 2, and 1, 2, 3 columns. Of course, they are numbered like row 0, row 1, column 0, column 1, column 2, as far as Python goes. All right. So, of course, you can also create zero arrays. We saw that in the previous video too. So you can create zero arrays. Like you want to create an array of zeros, or a matrix of zeros, if you like, that is 3 by 3. So that means you are going to have a 3 by 3 matrix that contains all zeros. So you just say np.0. So zeros is a function inside of NumPy. And then this 3 by 3 tells you the dimension of what you want to create. And then you see that you have a 3 by 3 matrix of just zeros. And you can do the same thing with ones. So you want to create an array filled with ones. So you just say ones underscore array. This is just a variable name. It could be anything, but this is sacrosanct. You can't change it. Like ones is actually a function inside NumPy, inside NumPy library. And then you want a 2 by 4 matrix containing just ones, and then you print the ones here, and then you have that. So you have 2 rows and 4 columns like that. All right. So you could actually also do you can create an array with a range of values, and that is where you use the function arange. All right. So arange is a function inside of the NumPy library. So range underscore array underscore arr is just a variable name, which could actually be anything. So you have range underscore arr equals np.arange 0, 10, 2. That means start from 0 and stop at 10. I mean, start from 0, keep increasing by 2 until you get to where you're going. But most of the times, where you start from the beginning, but you stop a step short of the big number. So it means you're not going to go as far as 10. So it means you are going to stop before 10. So that means you're going to have 0, 2, 4, 6, 8. The next thing after 8 should actually be 10, but 10 is usually excluded. So from 0 to 10, exclusive with step 2. So exclusive means 10 is not going to be part of it. Normally 10 should be there, but it's not going to be part because it is excluded normally. So you have 0, 2, 4, 6, 8. So you could actually use a range like that. And that is really efficient, right? Especially if you want to create something very long. For instance, let me do this. I create a new cell. Maybe I want to create, maybe I need all the multiples of 5 from 0 to 1,000. That's a lot, right? Imagine me having to write a list for that. So I need all the multiples of 5 from 0 to 1,000. Because I want 1,000 included, so I can add 1 to this. So it goes to 1,001 because I know it is going to stop a step short of 1,001. So I just run this. So you see everything goes from 0 down to 1,000. That's a lot, right? Imagine me having to write this one after the other. So, I mean, this makes it pretty easy. So a range is so powerful if you want to create something like that. Imagine I make it like 10,001. That's plenty, right? That's a lot. Okay, I mean, in fact, it is so big that it just shortens it up here. So let's do this. Let's leave it here. Okay, so that goes, right? So that's some possible ways by which you can create NumPy arrays. Now let's talk about some array operations. Of course, we can have element-wise operations like we saw in the previous video, but then we are just going to elaborate more here. But pay attention to this. We are not so once you have, all this array 1D, ARR1D, ARR2D, ARR1D is 1, 2, 3, 4, 5, ARR2D is 1, 2, 3, 4, 5, 6, 2 by 3, and you have all these other ones. So you can see that here we are not declaring new variables, we are not declaring new arrays because we are using those ones that are there, because ARR1D simply refers to this 1, 2, 3, 4, 5 we started with. So in case you're not seeing us declaring anything, once you've declared it at the top, you can always use it, except you now overwrite it with another declaration later. So for now, we are using just those array. So array 1D is 1, 2, 3, 4, 5. So if we talk about elements versus operation, so it means you're adding corresponding elements. So if you're adding array 1 to array 1, that's like 1 plus 1, 2 plus 2, 3 plus 3, 4 plus 4. So it's element by element correspondingly like that. And then you print the result of the addition. So, so this is going to give you like 2, 4, 6, 8, 2, 4, 6, 8, 10, or something like that, you know. And then array 1D minus array 1D, that's going to be all zeros, right? Because it's the same element being subtracted. And then you have array 1D multiplied by array 1. That's like 1 times 1, 2 times 2, 4 times 4, 3 times 3, up to 5 times 5 like that. And you can also have the division. This is going to be 1 all through, as you can imagine. So if we do that, see what we get. Of course, so you see array 1D plus array 1D, so it's like 1, 2, 3, 4, 5 plus 1, 2, 3, 4, 5, correspondingly, subtracting 0, 0, 0. Then here now, 1 times 1, 1, 2 times 2, 4, 3 times 3, 9, 4 times 4, 16, 5 times 5, 25. And array 1 divided by array 1, that's 1 divided by 1. I mean, each divided by itself, which is 1 all through. So you can do element-wise operations like that. So, and I mean, it doesn't take any special thing. Just do all this and you get the results. So we can actually have aggregation functions. So, I mean, the idea of aggregation is that you have a whole array and you want to get you have a value that represents the whole thing. That's aggregations. For the whole array, get one value. And don't forget, array 1 is to what we're working with. And array 1 is 1, 2, 3, 4, 5. So if you want to find array sum, I mean, this is just a variable name, ARR underscore sum. So you pick the sum function from the NumPy library. So you say np.sum. So you need to call this sum from NumPy library. So if you sum array 1, that's like adding from 1 to 5. And the very simple formula for that is go to the last number 5, multiplied by 6, that's 30, divided by 2, the answer is 15. So we expect to get 15 for this, right? Expect to get 15 for this. So if you want to add from 1 to any number, like you want to add from 1 to 56, just say 56 times 57 divided by 2. That'll be 28 times 57, and that's your answer. Okay. Then we also need the mean of all this now. Since everything is 5 and the sum is 15, so the mean is going to be 3, Then, of course, maximum value, we need the biggest value in that range. That's 1 to 5. So 5 is the biggest. Minimum, 1 is the smallest. That's the smallest. And if you run this now, you get those values: 15, 3, 5, and 1. Like that. So you can get all, you can get something representing a whole array like that. Okay. We can also talk about indexing and slicing. In fact, in a future video, we're going to focus strictly on indexing and slicing because there's more to it than this. Okay. For instance, you have array 1D, right? Now, array 1D contains numbers 1, 2, 3, 4, 5. So don't forget, counting in Python starts from 0. So array 1D 0 would be the first element, that's 1. Array 1D 1 will be 2. Array 1D 2 is going to be 3. So here now, it's more like array 1D 2 is like accessing the third element because counting starts from 0. So that means 3 is going to be the result of this. So if you print, of course, the variable name assigned to that is element. So if you run that, you get 3, So if you make it array 1D 0, that's 1. Array 1D 4, that's going to be 5, So here, we have array 1D 2, which is the third element like that, which is number 3. Okay, another thing is, so this is about accessing elements. What about slicing? Slicing is you're picking up a particular section of your array, So you say slice underscore ARR equals array 1D 1 to 4. Now so it means 1 full colon 4. That means from 1 to a step short of 4, because once you have an upper number like this, it is always exclusive. So it means you're moving from 1 to 3. I mean, you're moving from the first element. Sorry, you're moving from 1 to 4. That means that, okay, like if you run this now, it means the zeroth element is 1. So the first element is 2. You're moving from there to the third element, from the first to the third, because this fourth is actually exclusive. It's not part of it. So the upper thing is usually excluded. Pay attention to that. Okay. So you can also reshape arrays, right? You can reshape arrays. And if you are reshaping arrays, right, it has to be consistent with the number of elements involved. For instance, if you are reshaping something, that contains, say, 18 elements, so you can reshape it as 2 by 9, 9 by 2, 3 by 6, 6 by 3, 18 by 1, or 1 by 18, such that the number of row and column multiplied together must give you the total number of elements. If not, you won't be able to reshape. So if you are reshaping array 1D, it's normally array 1D is actually a 5 by 1, a 1 by 5 thing because it's 1 row and 5 columns. So you can reshape it as 5 by 1 like this, and then you get it this vertical. So you have 1, 2, 3, 4, 5. You can actually get to do that. Okay. So okay, I mean, let me quickly do something. I mean, the kind of example I gave, let's say we have let me think of something. So let's say range 1 equals okay, that a range thing, right? Let's say np dot a range, uh let me get that a range kind of thing, right? Yeah, np dot a range, and I need like 18 elements. Np dot a range, and I'm moving from say 1 to 19. That's like 1 to 18, and we are moving. Okay, well, if I'm moving by just one step, right, I don't have to worry. I know this is just from 1 to 18. And then the next thing is I want to reshape, right? So we just say I just say rest 1. That's reshape 1 now. And then it will just be that range underscore range underscore 1. And I'm reshaping. So I say reshape, reshape. And I want it to be 3 by 6 because I already know from 1 to 18 is 18 elements, right? So, okay, we can even print. Let's print range 1. So print range 1. Of course, this is not in the node that you download, so you can actually do this along. Then I also want to print res 1. That's reshape 1. Print res underscore 1. So, see what we get. Well, I can put a print in between, a blank print to give space so we can see more clearly. Okay, something like this. So, print range 1, that's actually from 1 to 18. You have that because I know everything is 18, right? So I can reshape it as 3 by 6. I can actually reshape it as 6 by 3. I can have Control V. So, of course, this was 1 by 18, right? So I can reshape it as 6 by 3, and see how it goes. Of course, I can, let me put this blank print here to separate everything. So, you can have this. So this is now 6 by 3. I can reshape. Okay, let me call this 2 now. Okay, I mean, it's the same range. So I just printing that. So I can have 6 by 3. I can actually have another reshape. I can reshape it in another way. I say reshape 3, and then it's 2 by 9, 2 rows, 9 columns, and then that's reshape 3. I'm printing right here. So 2 by 9. Okay, let me put this print to avoid it's just joining up. Okay, so you have this 2 by 9. I could also do 9 by 2, right? So I have this, that's res 4, and this, and that is, now I need 9 by 2, 9 by 2. So I have this. Okay, again, I need that print to separate it like this. So, I mean, we can have, initially we had 1 by 18. So we can, so the original thing is 1 by 18. So what if I want it to reshape it as 5, and then I want it to be 18 by 1. So I want it to be like a row, in a column rather than a row like what we first declared. So that's 18 by 1. And that is res 5. And then this goes. So it gives us that long thing. So don't forget the number of elements will determine the kind of reshaping you can do. So if you're reshaping something containing 20 elements, so you can reshape in 1 by 20, 20 by 1, 2 by 10, 10 by 2, 4 by 5, 5 by 4. You can do all of that. So that is what we have. So those are the ways to go. So you can also do broadcasting, right? Broadcasting scalar to array. For instance, you want to do an operation, you want to carry out an operation on every items in an array. So here we just say scalar broadcast. Don't forget array 1 is 1, 2, 3, 4, 5. So plus 1, that means you're adding 1 to every element. So if you print that scalar broadcast, you actually have 2, 3, 4, 5, 6. That means 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1, and 5 plus 1. That's why you have. So you can broadcast like that. So what if Okay, I guess we have some other kind of broadcasting later. Or let me just do something. So you have array 1D, like this. You have array 1D, and then you just want to add, maybe you want to square everything, or you want to raise everything by 3. And if you print that, see what you get. So 1 raised to power 3 is 3, 2 raised to power 3 is 8, and so on and so forth. You can do all that. Then you can do Boolean indexing. Boolean indexing. Of course, Boolean is a type of data type, is a data type actually in Python, and it's about true or false. So when a statement is evaluated, it tells you whether it is true or false, actually. So if you say bool underscore index, that's a variable name here. So now say array from array 1D, you want every element of array 1 that is greater than or equal to 3. Array 1D is 1, 2, 3, 4, 5. Greater than or equal to 3 will simply be 3, 4, 5. So if you print that now, you just get 3, 4, and 5. You just get 3, 4, 5 like that. So with that, we come to the idea of advanced operations. So far we've done creating NumPy arrays. We've seen different ways to create NumPy arrays. Then we've seen some basic array operations. So now let's look at some advanced operations. So let's talk about matrix multiplication. So you already know that NumPy, which is numerical Python, its strength lies in its possibility, the way it can work with arrays and matrices. So both one-dimensional and two-dimensional arrays. So two-dimensional arrays are more, better known as matrices, so to speak. So talking about matrix multiplication, for instance, of course, you may want to, in case you don't know how to multiply matrices normally, I have a whole playlist, like 26 videos on matrix multiplication, which you can check. Just check the playlist, you find matrices. Like if that's the first set of videos I started making when I started this channel. So you can go there to see how matrices are multiplied. So here you have mat1, which is matrix 1, and then you say np.array. So you have array, which is the function from NumPy, and then so you're creating that from a list of lists, and then it's going to be a 2 by 2 thing, and then you have the same thing of 4, 5, 6, and 7 and 8. So if you multiply both together, of course, I've put this blank print to create space, and then if you multiply both, you have mathmul, which is the matrix variable name, and then to do matrix multiplication, it's like you say np dot dot. So dot again is a function inside of NumPy, which makes for the multiplication of two matrices. So by the time you do this, see what you get. So you get 19, 22, 43, and 50. Okay. So that's how that goes. Then, of course, for the transpose of a matrix, we actually found another way of doing transpose yesterday. We just said something dot dot. But since you're using NumPy, to find transpose using NumPy, right? All you just do is you have the matrix transpose. So you already have matrix 1. You have matrix 1, which is 1, 2, 3, 4. 1, 2, 3, 4. So the transpose will just be this row becomes this column. This first row becomes first column, second row becomes second column. So 1, 2, 3, 4 will be like 1, 3, 2, 4. So that is it. So we can actually do the same thing for matmul. That's multiplication we got. Let me copy and paste this and then do this for matrix multiplication. So instead of 19, 22, 43, 50, we now have 19, 43, 22, 50 or so. That's what we get here. 19, 43, 22, 50. So this now, the first row becomes the first column, the second row becomes the second column, and that's what transpose is about. Then we can talk about concatenation. Concatenation simply means joining things together. So in the previous video, the video before this, right, we saw we could actually concatenate by just using a plus sign to add things up. But we could actually call the concatenate function inside of NumPy. So just a concatenated array will now be np.concatenate. That's array 1D, array 1D. So you're putting the two together, you know. So when you print that, see what you get. So it means you're just repeating it twice. So if you want it to come out right, you just have ARR1D again, and then you're going to have that 3 times. Of course, I think in where did you do this? I think on that list we could actually broadcast by just saying array 1D, raised power 3, star 3, and then it's just multiplies it. You just duplicate it those 3 times. So, I mean, there are different ways of doing the same thing. So it's all about how you want it. So we also have stacking in NumPy. So you can have vertical stacking or horizontal stacking. Now, what you have up here as concatenation is actually some kind of vertical stacking. So you see, you can actually use different ideas to do the same thing. But of course, at the end of the day, you have to settle for what works best, you know. So stacking arrays vertically, for instance, you have stacked array, you have np.vstack. So vstack is vertical stacking, and then you have this array1d in 3 places. So if you want to stack it vertically, it means you have 1, 2, 3, 4, 5 vertically, 1, 2, 3, 4, 5 vertically, 1, 2, 3, 4, 5, and it goes like that. And for the horizontal, it just come out like what we have up here now. So for this now, let's leave it at 2 that it was, because we have the case of 3, 3 here. So if you do this now, you see 1, 2, 3, 4, 5. You see it? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. But the horizontal stacking is all this thing like this. So that is about stacking. So you can actually stack stuff depending on what you need to do. So we talk about universal functions. Now, of course, these are all kinds of, like, you want to find sine, cosine, tangents, or exponents, or square root of all the elements in a particular array. And of course, we've been using array1d all the way. Array1d is 1, 2, 3, 4, 5. Don't forget that was what we declared first. So it's possible that if you want to work with some arrays, you want to keep working with these arrays. The first thing you want to do is, after you import NumPy as NP, then maybe in the following cell or even in the same cell, you just create those arrays you want to work with and keep referring to them. You don't have to keep writing out the arrays one after the each time you need to use them. Once you have declare them and you have run the cell, you can always refer to them, even in the 2001 cell in your Jupyter notebook. So here now we have array1d1. We are looking for the sine, the cosine, the cos, the sine, the cosine, the exponents, and the square roots. In fact, let me talk about the tan also. Let me add the tan to it. So say we also need the tan of the array. So I just copy this, bring it down here, you know, right, like this. And then what I need now is tan of the array. Tan of the array, that's TAN of the array. And this is tan. Okay. So we can run this now and we get all the results in one blow. Okay. Why do we have this? Okay. It's like I have too much space in between two. Not a problem actually, but just trying to be sure. Okay, so how many things are we doing here? Or better still, let me do it one after the other so we see the differences as they go. So here now, so I'm focusing on only sine. So you have sine of everything. Of course, you can be sure this is in in radians, right? So we can also talk about the cosine of the whole array. We can talk about the cosine of the whole array. Okay, I think we don't have print for cosine. That's the issue. So print cos array, cos array, cos array. Then I can take all this away and we see just for cos. So see that is for cos. And then I create another one. So again, we have, oh, I think I see the trouble now. So we need to print tan of the array. Okay, I think that was probably the issue I was observing. Okay, so this is for tan now. We want to find the tan of the whole array. So it means, even if you have 1,000 elements in that array, it is going to find a tan or whatever you are finding for everything all at once. So that's the beauty of this, right? It's going to find everything all at once. So here we are interested in finding the exponent. We want to find the exponent of the whole array. That is e raised to power x, right? That's e raised to power 1, e raised to power 2, and so on and so forth. So e raised to power 1, e raised to power 2, e raised to power 3, e raised to power 4, e raised to power 5. That's what we are looking for here. Of course, I know e raised to power 1 is like 2.718. E raised to power 2 also follows in that order. So you have 2.71, 7.38, 20, blah, blah, blah. It's exponential, so it grows very fast. So then, of course, we want to find the square root of 1, which is 1, square root of 2, which is square root 2, which is 1.414, square root of 3, 1.732, and so on and so forth. Square root of 4 is 2, square root of 5 is 2.36 or something like that. And you see what you have. So 1.414, excuse me, 1.732, and 2.236. like that. So you can actually do all of this together. Okay, so let's talk about statistical functions. Statistical functions. Say that, of course, yeah, we are still using the same array 1D, 1, 2, 3, 4, 5. So you want to find the standard deviation of the array 1D. You can do that. You want to find the variance. Of course, you know that variance is the square of standard deviation, and standard deviation is the square root of variance. You know that already. And then for the percentile, you want to find the percentile is when you divide a set of data into 100 equal parts. So the 50th percentile is just like the best of the top 50. I mean, the best of the bottom 50, actually, so, or which is more like the median also. So you can do things like that. So you can find the percentile. So if you run this, the standard deviation of 1, 2, 3, 4, 5 is 1 point square is root 2 actually. And then of course the variance is 2.0. So square of root 2 is 2, as you expect. And the 50th percentile, that's actually the median now, which is 3.0. So another percentile that is common. 50th percentile is also known as the median, right? And there's also the 75th percentile, which is the same thing as the third quartile. That is 4 now. Okay. So you can do things like this. All right. So we have random number generator. So sometimes you actually need some randomness. When you want, in a case where you want to be fair, like you want to give out a gift fairly, you don't want to have you want it to be as fair as possible. So you may need some randomness involved. So imagine you want to generate random numbers, a 3 by 3 random number between 0 and 1. So if you don't specify, it automatically takes it between 0 and 1. So it means it can give you decimal number. So if you do this now, you see you have a 3 by 3 matrix of random numbers. If you run it, it's random because if you run it again, the values keep changing. So if you want to do things like that, you can always do it. Okay. Then of course you want yeah, here I got really interested at, what if I want to create a 3 by 3 matrix? For instance, it's more like you have 9 seats. You have seats for 9 people. For instance, you as an exam person, maybe as an exam officer, I want to supervise 9 students and I want to scatter them as much as possible. So instead of me worrying my head too much, I can just do this and just keep running it until I get the perfect seating arrangement. So here now, because I need integers now, you can see previously we didn't specify integers. We just said np.random. Here it was just rand. Here it is rand int because we actually need integers. And it's from 0 to 10. Of course, that means from 0 to 9, and it has to be 3 by 3. So if I run this now, see what's happening. So, okay, it's just giving any number from between 0 and 10. So repetitions are there, like 2 zeros, 4, 3 nines, like that. So, I mean, this doesn't work for the exam scenario, actually. This is just, I mean, any numbers between 0 and from 0 to 9, actually. So that's working. But here, so I had to so here, I'm actually very concerned about no repetition of numbers. So here, I just say numbers is np.arrange. So range 9, that's from 0 to 8, right? So shuffle the numbers. You want to shuffle the numbers. So here, it's more like permutation. So just say np.random permutation of numbers. So permutation is still coming from random, which is also coming from NumPy. So in this case, now if I shuffle it, so it's actually strictly from 0 to 8. Or if I still want to stay with my 1 to 9, right? So that'll be like 1 to 10. So I have to specify 1 to 10 because I want 1 to 9 because the 9 is never reached. So if I keep shuffling, right? So you can see the numbers don't ever get repeated. The numbers don't ever get repeated, as you can see. So the numbers are unique all the way. So I can keep scattering like this to arrange what I want to arrange. So if you have more than 9 students, you can also do it. Like if you have 100 students, you can just write a simple code, especially if you have their matric numbers following in a particular range. So here, what I'm doing is I'm doing the same. I want a 6 by 3 thing because I know I'm from 1 to 9. 1 to 19 means 18. So here it's like from 1 to 18. 1 to 18. Here, let's leave it as the 0 to 8 that it was. 0 to 8 that it was. Because all of them have their different scenarios. Okay? So depending on what you want to do, you can decide how that works. So here now, I'm doing the same for 18. So you have 18 seats and you want them scattered. So you can keep running it because it is random, right? You can keep running it, and you get different arrangements each time you do that. All right. So that's that. Of course, finally, we come to linear algebra operations. So like you want to find the determinant of a matrix, the inverse of a matrix, eigenvalues and eigenvectors. All of this I already explained in my playlist on matrices. So you know you have matrix one already. Don't forget matrix one is that 1, 2, 3, 4. If you still remember, matrix one is this 1, 2, 3, 4. So of course, the determinant of 1, 2, 3, 4 is simply 1 times 4, 4 minus 6. 1 times 4 minus 3 times 2, that's 4 minus 6, that's minus 2. So here, we want to find the determinant of that, and we expect that to be minus 2. Then you want to find the inverse of that. Of course, I explained all of these things when I taught matrices, on its own, not in the computation sense. And of course, that's about eigenvalues and eigenvectors, all explained. So for matrix 1, 2, 3, 4, determinant, inverse, eigenvalues, eigenvectors, all that. So just in one blow, you get all that. Of course, this is minus 2.000 up to 4. I mean, you can ignore once you have many zeros like this, you can ignore all that part and just know your focus is minus 2. This is the inverse of that matrix. If you check the videos I previously made of matrices, you understand how to find inverses, eigenvalues, and eigenvectors. And with this, we come to the end of this very interesting video on NumPy arrays and operations. Once again, if you had not signed up to this channel, you want to do that, subscribe, hit the notification bell so you can always get alerted when a new video is released. Then make sure to comment. Maybe you want me to do something, or tell me I'm doing a great job. I don't mind, So comment, like, and share, so that more people can have access to these very useful resources. See you in the next video. Thanks for always stopping by.